You look so attractive when you're outside of your little squares. So some folks think that we need to go back to all the way to 7.1. Does that sound like where we need to be, a review of integrals? Yes? That's where we left off. Do you know how far we got? Whose job is it to know how far we got? Don't tell me it's mine. You do? I don't have anything. I made a list of the integrals we know how to do. And so there we go. There we go. Okay. But I don't think I have that little sheet on me, so I can't follow along on it. That's, oh, I do. Looky there. You think we got to about number 5. Okay. Do you want to ask anything? So where are we on web work? Do I have one closed that you need open? Is 7.1 still open?
7.1's due Wednesday. Yeah.
Okay, that's plenty of time. We can get it done today. Because it's a bunch of integrals that you already know how to do. So nobody's gonna ask anything? Good? Okay, so we're back at 7.1. Review basic integrals. And we've added some integrals to this list. We added, okay, so that's not fitting in the screen. Let me see how to make that fit the screen. Oh, it's backwards. Okay. Let me see how to fix the backwards thing. Huh. How do I fix the backwards thing? Mirror my video. Isn't that what we're doing? Put that away and see if that works. That works. Okay. That works. All right. Still not fitting us in here. That's probably just too close. Just such a bright thing. Maybe if I backed it up a bit. Or just right a bit. Okay, let's see. We're reviewing some basic integrals. And we've added some integrals to this list. Let's see. The integrals that most students tend to forget are the inverse trig functions. So let's see. We have the integral. I was going to write bigger and I didn't. It's okay, I can't erase. Here we go. Let's not go so far over there. Just stay to the middle of the board. Let's see, so we have this integral here. 1 over 1 plus u squared du. Remember that one? Which inverse trig function has this as its integral? That's an arctangent. That was the arctangent of u. If we change this from a 1 to another number, did we do that integral? Let's see what happens. What if we don't have something that's not a 1 here? Suppose we have something that looks like, I don't know, how about a 9 plus 4x squared? This has the similar appearance in that I've got the sum of two things in the denominator, and one of them has the variable squared. So that's where we need to think of how to make this look like that. So the first thing you can do is recognize that 4x squared is the same as the quantity 2x all squared. Okay. Then we need a 1 where the 9 is. So I'll just divide a 9 out from the denominator. Factor it out right here. That puts a 1 where I wanted it. But since there's not a 9 here, I've got to put a 9 in the denominator. Right here. Right? If I multiply that with that, I end up with the 2x all squared. Now that 9's a constant. It's a constant multiple of 1/9 that I can pull in front of the integral sign. Didn't leave room for it, but there it is. Then I'm going to write that 9 as a 3 so that I have a 2x over 3 all squared. Are you with me? So now we're going to do a Udu substitution. I'm going to take u to be the quantity in the parentheses. And then I take the derivative of that and get 2/3 times dx. So if I solve for dx, dx is 3/2 times du. And then I make that change. I've got the 1/9 out front. I'm going to have a 3/2 from the du term that I can put out with the 1/9. Then my integral looks like what I want it to. And so now I can say that that's the arctangent of u. Let's go ahead and cancel here. That's what, 1/6? And then u was 2/3 x. Okay. Now we could save us a handful of steps if I generalize this formula here. So that's what I'm going to do next. I'm going to change this to any number and write it as a perfect square. So I'm going to rub all this out here in a second. And I'm going to compute this integral, where this is an a squared. And that'll save us a bit of steps. So let's figure out what this is going to be by mimicking the steps that I did right here. A is just any number. So here my a was 3. Make sure you got this down because I'm about to erase this other stuff. Okay, so what we did last time is we factored out the a squared. So that's going to be my first step. I'm going to factor out an a squared from here. Let me rub that out. So I factor out a squared from there, and I'll put it out front as that. And that'll leave me 1 plus u squared over a squared. Then I'll think about u squared over a squared as the quantity, u over a all squared. And I'll pull the 1 over a squared out front. And now I'll do a change of variable. I already used a U, so let me use a W this time. I'm going to take W to be the stuff inside the parentheses. And the derivative of W is going to be 1 over A times the derivative of U, which puts us in A over here. So now, here's the 1 over A squared from the previous step. And this becomes 1 over 1 plus W squared. du is A times dw. So out front there, I can reduce the A times 1 over A squared to simply 1 over A. Then this is going to be the arctangent of W. Where W was U over A. Let's use that as a more general formula. Let's just remember that the integral of 1 over A squared plus U squared du will have a 1 over A out here, then the arctangent of U divided by A. And then we don't have to go through all of that stuff each time. This appears to have no audio. Let me check. Reagan, if you're out there, can you hear me? Turn this bad boy on. The audio just stopped, I think. Okay. Let's see why. What about now? Got any audio out there, Reagan? No. No audio. Okay. Let's select the camera microphone. How about now, Reagan? Hoorah! Thank you. Okay, we're back in business. Back in business. Okay, so we made a general formula, and it's not showing up on my camera, so let me scoot the camera over. There, we're going to make a general formula for all of our inverse trig functions. So if we have a variable out here squared plus the number squared plus the variable squared, and this can be in any order, right, because it's addition, then we can just jump right over here. So for instance, if we had that, we can jump straight to the antiderivative. Even though know that 7's not a perfect square, right? You have to think of that as being the square root of 7 all squared. And then you can just say, well, that should give us 1 over the square root of 7, arctangent of x over the square root of 7, right? So let's generalize all of our inverse trig formulas so that we don't have to do this manipulation here, factoring out the a. So the other one we had was for the inverse sine. The inverse sine and the inverse secant had square roots on them. The inverse sine integral has the variable behind the minus sign. So if I put an a squared here, well, it turns out this one doesn't have a 1 over a out front. It just has an arc sine of u divided by a plus c. And the reason for that is if I do that factoring by pulling out an a squared from in here, then when I take the square root of a squared, it's going to put an a in the denominator here. But then the step that I have here is going to generate an a that'll cancel the one out front. Can you kind of see that without me having to go through that derivation? So this is the only one that won't have a 1 over a out front. The inverse secant has the variable in front of the minus sign, but it also has the variable in front of the square root sign, something like this. So we'll have the variable here, and then here, squared minus a squared. So that one will have a 1 over a out front. That a comes from factoring out the a squared from underneath the radical. And so you have a 1 over a arc secant of u divided by a plus c. Can you move the monitor first? Yeah, sure. Maybe. Maybe not. How's that? No? Just quit writing in the corners what you're telling me to do. All right, let me see where I can write. How about I just write from here to here? All right, right in there. I don't know if I can see that part. Let's see if I can see it. Move the camera. So let's see if I've got one here that looks like an inverse secant. So what you need to do is recognize this as a potential inverse secant because the variable squared is under the radical sign and in front of the minus sign. And then we have the variable out front as well. So what I'm going to do is group the 25x squared together and write that as the quantity 5x all squared. Think of the 9 as being 3 squared. So one thing we need is that the term here is the same as the term there. So I'm going to go ahead and put a 5 right here and take it out by putting a 5 up there. Let me do that in another color. All right, so to make these two match, I'll put a 5 here, and I'll put a 5 up here. Now I'm going to do the Udu substitution, and I'm going to take U to be the 5x. And then du is 5 times dx. Well, that's kind of convenient because I have the 5 times dx right here. That's going to be my du term. So this looks like du over u square root of u squared minus 3 squared. I'm going to move the du over to here. And now it fits my formula. And the formula says I should get a 1 over 3 times the arc secant of u over 3 plus c. And then u was equal to 5x. Okay. So let's learn how to use the more general forms. You're going to see there's a lot in this chapter. So may as well get some practice on using them. Okay, so let's get away maybe from, well, I won't tell you, I'll just do some problems and see what you think of. So we've got a mixture of things that we have tried. Mainly we try to make things look like our basic integrals with a u du. So you got to know what you know. Make sure I've got a list of integrals that you supposedly know on Blackboard. If you pull that out while you're doing your web work or problems, maybe it'll help you remember them. Let's see what you think. Let's see what you think. If you know what you know. Does this look like an integral you know? Or can we make it look like an integral that you know? Yes, sir.
Is it like the cosine h over h?
That would kind of, that's a limit rule, but that's not one of the integrals we know. Right? Thinking of our integral formulas. Well, what do you recognize about this stuff compared to that stuff?
You can pull 1/6 out.
You can pull the 1/6 out. The 6 is baggage, right? So don't let that get in your way. But if you've got a square root in your integral, you're looking for if its derivative is also in the integral. What's the derivative of the square root of x? 1 over 2 square root of x. I've got a 1 over 2 square root of x hiding in here, don't I? So it's a u du integral. If I want a 2 square root of x, I'll have to pull just a 3 out instead of the 6. So let's rewrite that and pull out the 3 here. Write that as 1 over 2 square root of x dx. And then take u to be the square root of x that's nestled in there with the cosine. And then you said its derivative was 1 over 2 square root of x. So we've got a cosine of u du integral. What's the integral of the cosine? A positive sign or a negative sign? It's a positive. So we get the sine of u. And u was the square root of x. So there's one similar on your web work. You've got the sign of a fraction, and then it's got a denominator. Well, look to see what the derivative of the thing in the parentheses is. Do you have a sine of u integral? So it helps to recognize things like the derivative of the square root of x in simplified form is 1 over 2 square root of x. Okay, so the next one. One that they asked me about. Let's look at this one. It's also one similar to one that's on your web work. It's also one that you already know how to do.
Could we set u to x squared plus 16?
That'd be great. What if u is x squared plus 16? What's the derivative of x squared plus 16?
2x.
2x. So if this 4 wasn't here, then that's a straight u du integral, right? Or if this x wasn't here, what kind of integral we got? Arctangent. Well, they're both there, but they're in the numerator. So this integral behaves like a buy one, get one free. You've got two integrals that you know. You know how to integrate 4 over x squared plus 16. You know how to integrate x over x squared plus 16. So why don't we just break up the numerator and make two fractions? You can break up the numerator, you just can't break up the denominator. So let's rewrite this as 4 over the x squared plus 16. Then put the minus sign here and do the x over x squared plus 16. With the note that you're allowed to break up a numerator. Break that up into two fractions. We've got a common denominator. Rewrite it as two fractions with that common denominator. And then we'll do what you said you're going to do. You're going to write this as an arctangent integral and a UDU integral. This one's the straight arctangent. 4 is a constant, and my A is also a 4. So here's the constant that I'm pulling out. Then we should get a 1 over A term times the arctangent of x over A. For the next one, we were going to do the U sub. So we write U is x squared plus 16. So the du is 2x dx, which gives me a 1/2 du to replace the x dx. So minus, let me just call that integral star. We'll move that up over there. So let's go ahead and simplify that. 4 times 1/4 will give me 1. So we have the arctangent of x over 4. Then the next u du integral, I'm going to have the 1/2. This becomes a 1 over u du. Right? I took u to be the entire denominator. And the numerator came out with the 1/2 du. So that's a logarithm. And then replace the u with the x squared plus 16. Since x squared plus 16 is already positive, I don't really need the absolute value bars. Okay? You can break up the numerator. They're doing very similar. Keep it at a 16. That's an x cubed over the x squared plus 16. Oh, that's a dang blurry. What are your thoughts on this one? Can't see that x cubed. X cubed over x squared plus 16. But that's a single variable. There's no reason to place a single variable with a single variable, right? Because then you have a u plus 16 down in the denominator. Is that something you know how to do? We saw that we can do such an integral if the numerator had a constant or a first degree term. So the numerator is too big. That means we got an improper fraction. You can take a fraction like 27 over 5 and write that as 5 2/5. You can write that as a mixed fraction, right? Because the numerator is bigger than the denominator. When our numerator is bigger than the denominator, we can break this up as a mixed fraction just by dividing, right? 5 goes into 27 5 times with a remainder of 2. That remainder of 2 is 2 out of the 5 that's the divisor. If your degree on top is greater than or equal to the degree on the bottom, you can break that up as a whole part plus the remainder over the divisor. divide. Divide the bottom into the top. Make a whole part plus the remainder over the divisor. And see if then we have something that we can integrate. So I'm going to divide x cubed by x squared plus 16. Remember how to do that kind of stuff? Probably did it in 8th grade. Something like that. How many times x squared goes into x cubed? It goes x times. Then you multiply both of these terms by that x. And so we get an x cubed here, and we get a 16x here. And then just like in long division, you subtract that line from the line above it. And that gets rid of the x cubed and leaves me a negative 16x. And that's a remainder because x squared won't go into 16x. So that fraction has a whole part plus the remainder over the divisor. So we have that our integral looks like the whole part, which is the x, plus the remainder over the divisor. So again, you get two integrals. This one we can do right off the bat. This one we do with the Udu substitution. I'll take the 16 out front. The degree on top is 1 less than the degree on the bottom. So that tells me I have a straight Udu sub, where U is the entire bottom. Du is 2x dx. So we hang on to that x from the numerator and replace it with 1/2 du. So I'm going to give half that, say that again real slow. I'm going to get a factor of 1/2 out here with my 16. So let's go ahead and make that an 8. And this becomes a 1 over u du integral. The integral of 1 over u is the natural log of u. And u was x squared plus 16. Again, x squared plus 16 is positive, so we just get rid of the absolute value bars. So let's make that a general rule. If you're trying to integrate a fraction, make sure your fraction's in reduced form, in the sense that the degree on top is strictly smaller than the degree on the bottom. If you ever have the degree on top the same degree as the bottom or more, then this dividing thing is the way you're going to want to go. Okay? We haven't done yet? Integration fun? Yeah, baby. I like that. I like that enthusiasm. Okay. Next one. Next one, next one, next one. Problem bring out any thoughts, comments? Anything going on up there in your little heads?
Should we factor the bottom factor?
Okay, are there any factors of 25 that add to 8? Not a chance, right? So trying to factor is a good idea, but we can't. There are no factors of 25 that add to 8. Anything else you want to do with a
We just make the denominator to x plus 4 squared plus 9.
complete the square? Good. Complete the square. We're going to complete the square in the x squared plus 8x plus 25 by writing the polynomial like this. Leave a gap. In completing the square, you add something here, but you got to take it back out right here. And you're looking for something that factors as a perfect square, so that whatever number I put here, it has two factors that add to 8. Two identical factors that add to 8. 4 plus 4, right? So the number 16 has the factors of 4 plus 4. We put the 16 in here, we take it out there. There was a mindless way that you can always remember what goes in here. Whatever this middle term is, you cut it in half and then square it. Put it in each box. Put it in, take it out. That'll make that first batch factor as a perfect square. This is x plus 4 all squared, and then 25 minus 16 is 9. So I can rewrite this integral as x plus 4 squared plus 9. Does that look like anything you know how to do?
Looks like a arctangent.
It's an arctangent. We take u to be x plus 4. Du then is dx. And it's 1 times du over u squared plus 9. So according to this formula, I should get 1 over 3 times the arctangent of u over 3. Where u is x plus 4. So add the completing the square to your bag of tricks. See if you can make it look like one of those. Okay. One over 1 plus e to the negative x dx. Okay, so if you try to make it look like a 1 over u integral, you've got a problem, right? Because if you take u to be the entire denominator, what is its derivative? What's the derivative of 1 plus e to the negative x? Negative e to the negative x dx. And I don't have that in there. I could try putting it in and taking it out. If I multiply top and bottom by e to the negative x, does that help? Let's try. Well, that gives me a problem. It does give me the e to the negative x on top that I need, but then it gives me two versions of the e downstairs. That looks worse than what I started with. This guy has its derivative up there, but this guy doesn't. So that's not going to work. Right? Can you see that that's not going to give me an integral any better than the one I had before? But I want you to keep in the same train of thought of multiplying by 1. Is there a better version of multiplying by 1 than this? This is the icky part. Is there a way we can avoid that?
Multiply by 1 plus e to the negative x.
Multiply by itself?
No, by the entire denominator.
Top and bottom?
Yes.
Let's give it a shot and see what happens. So try the UDU thing. So you take U to be the stuff inside, and I don't quite get the stuff on top. Close. We're close. But we got that extra one there. So I can't do the UDU sub from that place either. So that's another ARG.
Make it 1 squared plus e to the negative x over 2 squared.
Okay, where am I going? 1 squared plus e to the negative x over 2 squared. Then I would need an e to the negative x over 2 on top. Good. That one's going to work. Because what do you get when you multiply e to the x with e to the negative x? E to the x times e to the negative x. That's 1. Right? You add powers, you get e to the 0, which is 1. So that's going to get rid of this extra term that we got stuck with here. If we just change this to e to the x over e to the x. Kind of think of that as some version of the conjugate. So try number 3 is to knock off the minus sign and see if we can make our integrand look. See, it's still multiplying by 1. Again, that's legal in every state, including Arkansas. So we can get an equivalent expression. So when I multiply this out, it gives me an e to the x on top, gives me the e to the x here, but it gives me a 1 right there. That's good news. If I have an e to the x in the denominator, then I'm going to need the exact same term in the numerator, or maybe one that's the square of that. But this is going to work. This fraction is equivalent to this one. Now I can do a Udu substitution. And that's what we're doing to get from there to there. So we take u to be the whole denominator. The derivative of u gives me the numerator. So now I have a 1 over u du integral. It'll give me the natural log of u plus c. And u is 1 plus e to the x. 1 plus e to the x is always positive. So So I can go ahead and use parentheses instead. Okay? If you've got an e somewhere in your integral, you're going to need some version of that e in the numerator. So put it there and take it out, right? By multiplying by 1. Okay, one more, and then we'll move on to the next section. Is this my long day or my short day? I heard two different answers. Which day is it, long day or short day? Is the short one. Bummer. I'll stay if you'll stay. Okay, next one, next one, next one, next one. I bet you know how to do this one. I bet you $1 you know how to do this one. Let's take x squared times the square root of x plus 1. So maybe you can just go ahead and replace the square root sign with a 1/2 power. That seems like a natural place to start. That dang x squared weren't out in front. I've got a UDU integral, right? But that x squared is out front. Any ideas here? If I distribute it, I have to bring in like an x to the 4th, right? Because that's x squared. If I want to bring it into a square root, so I'd have to write that as the square root of x to the 4th. And then I'd have an x to the 5th plus an x to the 4th. That's uglier. It would be nice if I could distribute, and I will be able to distribute with a Udu substitution. I take u to be the stuff inside, and then the derivative of u is just dx. But again, this is uncovered. What am I going to do with this x? Let's find out. Here's x. So x is u minus 1, right? I do a u, du, and an x substitution. Now let's rewrite the integral and see if distributing is a better option. The x squared becomes u minus 1 all squared. The x plus 1 to the 1/2 becomes u to the 1/2. Now my quantity has the integer exponent. Now I can expand it. Right? I can't expand that. I can't write that as x to the 1/2 plus 1 to the 1/2. Can't do that. But I can square something pretty easily. I can just multiply this thing out now. Right? This is u squared minus 2u plus 1, and then we'll distribute. Send that u to the 1/2 through there, and then we'll be able to integrate term by term. Remember, when you multiply like bases, you add the exponents. So 2 plus 1/2 is what, 5/2? 1 plus 1/2 is 3/2. And then 1 times u to the 1/2 is u to the 1/2. Now I've got them all separated. Just integrate with power rule each time. We get u to the 7/2, and when I divide by 7/2, that puts a 2/7 out here. Well, this 2 out, This becomes u to the 5/2, put a 2/3 right here. This becomes u to the 3/2, put a 2/3. Oops, that should be a 2/5 right here. I'm kind of thinking ahead. That one's a 2/3. And then let's replace the u and we're done. So let's go over here. We get 2/7 times x plus 1 to the 7/2. Let's make that a 4/5 x plus 1 to the 5/2 plus 2/3 x plus 1 to the 3/2 plus c. I call this a double substitution because I did the ordinary UDU and then I had to get something for the extra x. And this double substitution arises when the stuff inside the rule is smaller than the stuff outside the rule, smaller in degree. Usually we want it to be one more in degree so an ordinary UDU substitution works. But if it's backwards, then you do this double substitution. You did that in Cal 1, didn't you? My Cal 1 students, you're supposed to. So there's a lot of integrals that you know how to do, but they involve a little algebra, little nips and tucks to get them into the ones you know how to do. Primarily, integrals that are products, if they aren't UDU integrals, involve using something called integration by parts. So I'm going to show you integration by parts now. Can I rub all this stuff off? See how far this thing goes. We'll go all the way to that dotted line there. How did you guys hold up during the great winter storm? You stay inside, you can play in the snow. Did you go home? Everybody was okay? How's your family? Anybody from Houston? Houston had a heck of a time. How was your family? They did okay? They had electricity? Yeah. Jeez. My son is in Houston and he was without electricity for 3 days.
How did he stay warm?
He has a girlfriend. She has a dog. You know how dogs kind of spoon you and keep you warm. Now he said, well, let's go and visit my other son who lives in Brownsville, which has to be warm because that's as far South Texas as you can possibly get. So he loaded up and girlfriend and the dog and drove to Brownsville. The day they got there, Brownsville started their rolling blackouts. So they had no electricity for another day. But at least it was warm there. So no electricity in a warm house is better than no electricity in a cold house. But I was cold and I had electricity. So I just had like lots of clothes on. I was that kid from Christmas Story.
My parents still don't have hot water.
Really? Where are they?
I'm making sense.
Really? Holy smokes. Holy smokes. That's too bad. How many days have it been?
Since like the beginning of last week.
Yeah, it's pretty bad. It's like we live in a third world country with all this technology in here.
Yeah.
Okay, here's integration by parts. Section 7.2. One of the important things is to recognize when to use what. So I'm going to let it cat out of the bag. Integration by parts works best if you've got a sine or a cosine multiplied by some polynomial term, or an e or a logarithm multiplied by a polynomial term, or any of our inverse trig functions as the integrand. So if you have an x to a power times a cosine or a sine, or an x to a power times an e. If you have any version of a logarithm, whether it's a logarithm by itself or an x to a power times a logarithm, because we don't have an integration formula for a logarithm. The other things we don't have integral formulas for is if the integrand itself is an inverse trig function. Or you can even put a polynomial in front of any of these. Anything with a logarithm, inverse trig function, inside your integral, if it's by itself, right? If its derivative is in there, it's u du. But if it's by itself, this thing that's called integration by parts is going to work. And integration by parts is simply the product rule. Let's take two functions and multiply them together. I'm going to let u be some function of x and v be another function of x. And so if I take the derivative with respect to x of the product of those two functions by the product rule, I hold one, take the derivative of the other one. I don't want to put the of x. First times the derivative of the second plus the second times the derivative of the first. Now I'm going to take that line and I'm going to integrate both sides with respect to x. And so I'm going to integrate right here. With respect to x. So we'll have the integral d over dx of u times v. Now here's what I'm integrating with respect to x. Integrate this, and then integrate this. But this says we're integrating the derivative of something. What happens when you integrate the derivative of something?
It's just that.
It's just that, right? So over here, I just get u times v. Over here, I get all this stuff. I'm going to take this equation and solve it for this term right here. So if I keep that here and subtract this from the other side, I'm going to have that this integral is equal to u times v minus the integral of v times u prime of times dx. And so I'll write that up here, that the integral of u v prime dx is equal to that minus that. It looks like I got too many variables, so let me write it like this. Let's write this as the integral of u dv is equal to u v minus the integral of v du, where dv is v prime times dx and du is u prime times dx. This is our integration by parts formula. Integration by parts formula. If your product has the form of the product of two functions, where one function you know its derivative, and one function you know its antiderivative, then you can spread it out like this and hopefully get a second integral that's easier to do. So here's what I mean by the product of two functions. If that x weren't there, that's a cosine of whatever integral. I can do that. But that x is there, so it throws me off. That x is not the derivative of what's inside, so it's not an Udu substitution. It has the part of a polynomial times a trig. So I name these two parts u and dv, where dv is the part that I know how to integrate, and u is the part I know how to differentiate. I know how to integrate both of these, but the bigger part is the cosine. So I'm going to take that as dv. So I'm going to let u be x and dv be the cosine of 2x times dx. I want to make sure everything's taken care of. X is here. That part goes with the dv. And I need to generate the other terms. I need to generate a du, which is the derivative of this line. And I need to generate a v, which is the integral of this line. So I take the derivative here and get du is equal to dx. And I take the antiderivative here. I integrate. So here's the step I'm doing in my head. I'll do it up here in blue. The integral of 1 times dv is going to be equal to the integral of this cosine of 2x dx. That's the part I'm doing to get from here to here. So you agree if I integrate just a 1 with respect to v, I get v. What do you get when you integrate a cosine of 2x? Sine of 2x over 2. Now I employ my formula. Let me erase this muck over here. It says to expand the product of the cosine of u, the cosine of x times the cosine of 2x as our uv minus the integral of v du. So let's put our parts in the right spots. Our u is x, and our v is the sine of 2x over 2. Minus the integral of v. V again is the sine of 2x over 2. And du is just dx. Is this an easier integral? Get that 2 out front. We're integrating sine of 2x. We can do that, right? What's the integral of the sine of 2x? Negative cosine of 2x over 2. And we're done. You can clean that up and put the two minus signs together. Half times a half is a fourth. We can simplify that as x sine of 2x over 2 plus cosine of 2x over 4. Right? So this is the antiderivative of that, which means if we took the derivative here, we should be able to simplify it all the way to this. Of course, the derivative is going to take a product rule action here, but we can do it, right? Let's do it in our head. Let's think of x over 2 as the first term, times the derivative of the second. What's the derivative of the sine of 2x? 2 cosine 2x. So this will simplify as x cosine 2x in that half of the product rule. Now the second half of the product rule is the sine of 2x times x over the derivative of x over 2. We get a 1/2. So we get 1/2 cosine of 2x. Now we're going to take the derivative here. I don't think I can do it in my head. Then we get a sine of 2x times 1/2. When I take the derivative here, I'm going to get another. We get a negative sine of 2x times a 2, so that'll be times 1/2. That negative and that negative add each other out, and we have that back. Okay. All right, so let's do an integral of an x to a power times a logarithm. Let's even grab a funky power. How about a 3/2 power? Usually when there's a logarithm in our integral, we hope that there's a 1 over x in our integral as well, so that we'd have a UDU. Well, I don't have a 1 over x. I've got a product of a polynomial and a logarithm. So that tells you you've got integration by parts. If the logarithm is an integral, it has to be the u, because we don't know what the integral of the natural log of x is. We only know its derivative. So this part is the u. Everything else has to be the dv. Write your integral as a product of a u with a dv. So if this is the u, everything else is the dv. Then to get the other terms in the formula, we have to take the derivative of both sides here, the antiderivative of both sides here. So the derivative line would look like du is 1 over x dx. Now we integrate. The integral of dv gives me v. We're integrating x to the 3/2. So you add 1 to the power and divide by the new power. You add 1 to 3/2, you get 5/2. When you divide by 5/2, you get a 2/5 here. So I have all 4 terms that are required for the formula. Let's go ahead and expand. So the integration by parts formula says I multiply uv minus the integral of v du. I'll keep writing that down so that you can learn it. U times v is the natural log of x times 2/5 x to the 5/2. Minus the integral of v, well, v is the 2/5, x to the 5/2, times du. And du is 1 over x dx. That second integral is still kind of messy. Let's clean it up a little bit to see if we know how to integrate it. We can clean it up by getting this outside and multiplying those two together. I also like to write my polynomial term in front of everything else. So let me swap the order of those two. Then I won't need parentheses. So when I multiply here, what does that simplify to? X to the 5/2 times 1 over x. What's my power going to be right here? 3 over 2. That's an integral I know how to do. I did that just a second ago. So now complete this integral, and we're done. All right, so integrate x to the 3/2, you add 1 to the power, so again, that's a 5/2. Divide by that puts a 2/5 right here. And there's our antiderivative. Yes, sir.
Would we ever have to do by parts inside of itself?
Yep. Yep.
So how do you decide what you're gonna like take you to?
That's the hardest part. I always try to pick dv first. dv has to be the biggest part of the integral that you know how to integrate if it were by itself. So here I had no choice. I don't know how to integrate the log of x. So I had no choice. If I pick this part first, then that part's just everything else. Look at it and see if that wasn't there, could I integrate it? With practice, it'll be more obvious. Most of the time, like when you have the x to a power times sine or cosine, you always pick dv to be the sine or cosine and u to be the x to the power. Here it was backwards because I was forced to pick this to be the dv. Okay? But given the choice, I would rather the polynomial term be here because its derivative is 1 power less, and its derivative shows up over here. I always like the 1 power less here. But that comes with practice, which you're going to do a lot of. So you wanted to see one that had integration by parts more than once? I got one. Let's keep the x. Let's go with an x cubed times an e to the x. Now, if that x weren't there, I can integrate e to the x. If the e weren't there, I can integrate x cubed. But of the two, the e to the x is the more substantial term. So that's the part I picked to be the dv. And then the u is the x cubed. To get the du, I take the derivative of this line. So du is going to be 3x squared times dx. To get the v term, I integrate this line. What's the integral of e to the x dx? Just e to the x. So now let's expand this out with our formula. We need a u v minus the integral, oh, that's sad, of v du. So u v gives me an x cubed e to the x out front, minus the integral of v is e to the x, and du is 3x squared dx. Again, I like to put the polynomial term in front. So let me change the order here. So my resulting integral from the formula is almost like the integral I started with. It still has this pesky polynomial term here. So I did integration by parts again. Keep with your same format. I picked u to be the polynomial term earlier. I'm going to pick u to be the 3x squared here. So I'm going to write down I'm doing this for the second time. The spoiler alert, there's going to be a third time. I'm going to take u to be the 3x squared and dv to be everything else, e to the x dx. Then we take the derivative of this first line to get du is 6x dx. we take the antiderivative of that line. So we get v is e to the x. Okay? All right, so let's pull it up here. The x cubed e to the x is part of the antiderivative, so keep it. Now I'm going to put my integration by parts scheme right here. U v minus the integral of v du. I put the brackets because the minus sign has to go on both of these guys. So u v gives me a 3x squared e to the x minus the integral of v times du. So I'm already going to write it in the reverse order. I'm going to write v times du as 6x e to the x dx. Okay? And so I don't lose the minus sign. I'm going to go ahead and distribute it now and get rid of these brackets. So that now becomes a plus 6x e to the x dx. And I know from experience that this is another integration by parts because I have a polynomial times an e to the x. But hopefully it'll be the last one, right? Because my du term is going to go down in degree. So here we're going to do integration by parts again. And so our third time on that one, we still pick u to be the 6x and the dv to be everything else. The derivative of the 6x gives me a 6 dx, and the v gives me an e to the x. So fortunately, this is the last one. Let's put it in here. We keep the first two terms. Those are part of our antiderivative. And in here we put uv minus the integral of v du from our third time through. And so we get 6x times e to the x minus v is e to the x times du. Du is just 6 dx. One more integral to do, but this one is straightforward. 6 is just a constant. The integral of e to the x is e to the x. So, big drum roll, here's the finish. X cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 6 e to the x plus c. Guess how many times we'd have to do integration by parts if this were to the 5th power? And it's kind of redundant. I'm going to show you how to do all of these steps in a nice little table next time, because we're out of time here. You can do multiple integration by parts in table form if you have a polynomial that eventually has a derivative of 0. So get started on the 7-1 homework, and if you seem that you need more time, just let me know and I'll open it longer. But you're not doing anything now, right? All your tests were last week. Now it's just all calculus. Huh. Were they? Weenies. Okay, so I think I'm done here. Reagan, Don, let's leave.